Take two metal plates. No charge running through them. No wires. No mechanism. No battery hidden anywhere in the setup. Seal them inside a perfect vacuum. Every molecule of air pumped out. Every stray particle stripped away. So there's genuinely nothing left between them but empty space. Now bring them close. Closer than a human hair. Closer than a single red blood cell. Close enough that the gap is measured in nanometers. And they start moving toward each other. On their own, there's no current, no magnetism, no leftover gas pressure, no vibration from outside the chamber. By every classical rule of physics you were ever taught, two neutral, uncharged plates sitting in a true vacuum should just stay exactly where you put them. Forever. Nothing should touch them, because there is nothing there to touch them. They move anyway. This isn't a thought experiment, and it isn't a rounding error. It's been measured in real labs, down to fractions of a nanometer, using some of the most sensitive force sensors ever built. Instruments precise enough to detect a force thousands of times smaller than the weight of a single grain of sand. Physicists call it the Casimir effect, first predicted in 1948 by a Dutch physicist studying colloidal chemistry, of all things, and it's forcing us to admit something deeply strange about the universe. Empty space isn't empty. Here's the part that breaks people's intuition. Quantum physics says a true, perfect vacuum. Zero particles, zero energy, absolute nothing, cannot exist even in principle. Even in the emptiest possible patch of space, far from any star or planet, particles are constantly flickering in and out of existence, popping into being for a fraction of an instant, then vanishing again before they can even be called real. Scientists call this quantum foam, or the zero-point energy of the vacuum. It's not matter. It's not stuff in any normal sense. It's activity, the baseline hum of reality itself, running underneath everything, even when there's nothing left to hum. So what does that have to do with two metal plates? Between the plates, only certain sizes of that quantum flickering are allowed to exist. Think of a guitar string that can only vibrate in specific wavelengths once you pin down both ends. Pin the ends closer together and fewer wavelengths fit. Outside the plates, in the open vacuum, there's no pinning down anything. Every possible wavelength is allowed to exist unrestricted. That means there's slightly more quantum activity pressing in from the outside than there is squeezed into the narrow gap between the plates. And that tiny imbalance in pressure, multiplied across the entire surface of the plates, is enough to physically shove them together. Nothing is pushing them. Except nothing, it turns out, has structure. Nothing has pressure. Nothing, apparently, can shove. At everyday distances, this force is far too weak to notice. You will never feel it holding your coffee cup to the table, and it plays no role in ordinary life. But at the nanometer scale, where these experiments are run, it becomes one of the dominant forces in the entire system, easily strong enough to overpower gravity at that range. Engineers building the tiniest machines on Earth, microscopic sensors, nanoscale mechanical switches, the guts of next-generation microchips, have a design around it because at that scale, the vacuum itself starts pulling their moving components together, sometimes permanently causing tiny parts to seize up and stick, a phenomenon engineers call stiction. It's a real, practical constraint on manufacturing, caused entirely by empty space. But the real reason physicists obsess over this effect isn't nanotechnology. It's the sky. If empty space genuinely has energy built into it, measurable, real, provable with nothing more than two plates in a lab, then that same energy should exist everywhere in the universe, filling every cubic centimeter of space between every galaxy right now, whether or not anyone is there to measure it. And physics lets you actually calculate, roughly, how much energy that should be. Here's where it gets almost impossible to believe. When scientists calculate the vacuum's predicted energy using quantum field theory, then compare it to the actual energy driving the accelerating expansion of a universe, the mysterious force cosmologists call dark energy, the two values don't just disagree. They disagree by a staggering margin, widely cited as one of the largest mismatches between theory and observation in the entire history of physics. Some estimates put the gap at many dozens of orders of magnitude, a difference so large it's genuinely hard to put into everyday language. Something in that chain of logic is wrong, or missing, or fundamentally misunderstood, and right now, nobody knows exactly which. It's one of the most cited open problems in modern cosmology, sometimes called the cosmological constant problem. The same quantum weirdness that gently pushes two lab plates together might be a genuine clue to why the universe itself is expanding faster and faster, pulling galaxies apart. Or it might be a coincidence of the math that's quietly misleading an entire field of science. Right now, serious researchers argue both sides, and no experiment has settled it. So next time someone tells you empty space is just empty, picture two plates sealed in a vacuum, quietly drifting toward each other with no visible cause, pushed by a force made of nothing. A force that might be tangled up in the same mystery that's tearing galaxies away from each other, right now, faster every single second. We prove the vacuum isn't silent. We just don't fully know what it's trying to tell us. If you had to bet, is the vacuum's hidden energy the missing piece of dark energy, or a coincidence that's fooling some of the smartest physicists alive? Tell me your theory below.